Imagine if time isn't what we've always thought it to be. Kaku, a renowned physicist, shook the very foundation of our understanding when he claimed that time does not exist. Time and space, he suggested, are like a fabric, elastic, like rubber, or a trampoline net. Recent revelations from the James Webb Space Telescope have added a surprising twist to this discussion. Peering into the depths of the universe, this groundbreaking telescope has uncovered findings that seem to support Kaku's theory. Among its discoveries are 6 galaxies that existed 500 million years after the Big Bang. It's as if we've discovered a whole new layer to the universe we thought we understood. The James Webb Space Telescope, JWST, launched on Christmas Day 2021, is a larger, more advanced version of the Hubble Space Telescope. Placed in space, it reveals hidden mysteries from the farthest corners of the universe. Equipped with powerful infrared instruments, it acts like a time machine, letting us peer into the past. Its incredible resolution and sensitivity allow it to spot ancient and faint objects that even Hubble couldn't detect, such as distant galaxies and celestial bodies from the early universe. These elusive entities, which have long challenged us in a cosmic game of hide-and-seek, are now being revealed one infrared image at a time, solving the universe's intricate puzzle piece by piece. Imagine being in an art gallery, admiring stunning pictures taken by the James Webb Space Telescope. Across the cosmic canvas, distant galaxies shimmer in breathtaking detail. Yet, among astronomers and cosmologists, there is a mix of shock and disbelief. These stunning images challenge the very foundations of a long-held theory, the Big Bang hypothesis. This theory posits that the universe began with a massive explosion around 14 billion years ago and has been expanding ever since. It has served as the cornerstone of cosmological understanding, but the new images from JWST appear to challenge its accuracy. The galaxies captured in these images are smaller, smoother, older, and far more abundant than the Big Bang hypothesis predicts. This discrepancy has left researchers like Alison Kirkpatrick, an experienced astronomer, questioning the very essence of their life's work. The unease among scientists arises from these galaxies' unexpected behavior, which challenges the established understanding of the cosmos. According to the expanding universe model, far-off galaxies should appear smaller as they move away from us. However, after a certain point, they should begin to look bigger because their light left them when they were closer to us. The James Webb Space Telescope has thrown a curveball into this assumption. Its images show galaxies that appear to be the same size as those closer to us. It's like expecting distant friends on the horizon to look tiny but finding them as large and vivid as those standing right beside you. Adding to the mystery, these galaxies, despite being brighter and having more mass than our own Milky Way, appear 2 to 3 times smaller in JWST images compared to Hubble's. Furthermore, they seem to be moving away faster, indicated by their high redshifts, a phenomenon that aligns with an expanding universe. Yet, the images suggest something different. In fact, scientists first noticed this anomaly back in 2014 with Hubble images. Galaxies with certain redshifts appeared as if they existed in a non-expanding space. The JWST has only amplified this puzzling trend. Even galaxies with high redshifts, such as 12, show similar sizes, defying expectations based on the Big Bang model. In simpler terms, the JWST's images suggest that faraway galaxies might not be influenced by the universe's expansion as previously thought. This contradiction challenges the Big Bang theory's assertion of an ever-expanding universe. If the theory holds, these galaxies would need to be incredibly tiny to account for the illusion created by expansion. It's as if the puzzle pieces simply refuse to fit, leaving scientists grappling for answers. Consider the example of a galaxy named GHZ2, observed by the James Webb Space Telescope. It is much brighter than the Milky Way but calculated to be only 300 light-years wide compared to the Milky Way's 50,000 light-year span. Its brightness per unit area is 600 times greater than the brightest galaxy near us. Additionally, GHZ2 and similar galaxies are incredibly dense, thousands of times denser than familiar galaxies. These discoveries challenge our understanding of the expanding universe and the Big Bang theory, sparking new debates among astronomers and cosmologists. The Hubble Space Telescope had previously revealed many such dense and powerful galaxies, likened to Mighty Mouse from old cartoons. Now, with the advanced capabilities of the James Webb Space Telescope, the puzzle has only grown more complex. To make sense of these unusually compact galaxies, scientists have proposed ideas akin to magical toy cars, tiny in size yet carrying immense weight, defying conventional expectations. With each new discovery, the James Webb Space Telescope reshapes our understanding of the cosmos, leaving us to wonder what other mysteries it will unveil. They propose that these microgalaxies collide with each other over billions of years, merging to form the larger galaxies we see today. It's as if toy cars collide and grow into real SUVs over time. However, the James Webb Space Telescope, JWST, has closely examined these galaxies and found no evidence of such cosmic collisions. If galaxies were crashing into each other, we would expect to see some signs of damage, perhaps some disarray or distortion, much like a car after a small accident. But that's not what the JWST has observed. Instead, it reveals galaxies that are smooth and neat, resembling the ones nearby. There's a lack of any visible damage or collisions among these galaxies. One study, aptly named Panic, points out that there are 10 times more of these clean spiral galaxies than theorists had predicted. This discovery is like finding a busy highway with fast-moving cars but no accidents. It challenges the collision theory. Without signs of galactic mergers, the idea that these small galaxies expanded into larger ones falls apart. If they didn't grow in size, it suggests they weren't small to start with. As a result, the expected optical effects from an expanding universe seem to be missing. Without this expected illusion, the concept of expansion loses support, leading to growing unease among proponents of the Big Bang theory. The presence of these small, smooth galaxies suggests that the universe might not be expanding, and if it isn't, the Big Bang theory faces a significant challenge. Recent discoveries in astronomy have set the stage for a significant reconsideration of our understanding of the universe's origins. The Big Bang theory has long been the cornerstone of our comprehension of how everything came into existence. It posits that the universe originated from a colossal explosion, yet emerging evidence seems to suggest a different narrative, one that could revolutionize our comprehension of cosmic history. Enter the JWST, often likened to a time machine by experts like Michio Kaku. This incredible device possesses the capability to peer billions of years back into the cosmos. Its groundbreaking capacity lies in capturing images far beyond the reach of our naked eye, delving into the infrared spectrum rather than the conventional visual spectrum. What's captivating about these images is their ability to reveal the enigmatic story of distant galaxies. The colors captured by the JWST are not just aesthetically pleasing, they encode crucial information about the ages of stars within these galaxies. For instance, youthful, fiery stars blaze a vivid blue, while their older, cooler counterparts emit hues of yellow and red, akin to our Sun. By analyzing these colors, astronomers can estimate the age of star populations within these distant celestial bodies. However, here's where things get intriguingly puzzling. Some of these observed galaxies seem to house stars that predate the supposed age of the universe itself as per the Big Bang theory. This discrepancy challenges a fundamental tenet of the theory, which posits that nothing should exist older than the Big Bang. Moreover, according to the theory, as telescopes like the JWST gaze farther into space, effectively peering back in time, there should be a diminishing number of observable galaxies until reaching a point where none exist, a cosmic dark age. However, contrary to this expectation, the JWST observations suggest a different narrative. Galaxies as massive as our Milky Way were seemingly common just a few 100 million years post the presumed Big Bang event. The implications of these observations are profound. The images obtained by the JWST indicate a startling revelation. There appear to be approximately 100,000 times more galaxies at high redshifts, more than 10, than initially predicted. This abundance of large galaxies challenges the established understanding of the universe's formation within the constraints of the Big Bang theory. The emergence of so many colossal galaxies in such a relatively brief time span raises pertinent questions that challenge our existing knowledge. How could these sizable galaxies form and evolve in what was deemed an insufficient timeframe according to the conventional model? These groundbreaking discoveries pose a challenge to the foundational principles upon which our comprehension of the universe rests, inviting scientists to re-examine and reconsider our understanding of cosmic origins. Recent research has thrown a fascinating curveball into our understanding of cosmic origins, suggesting that the venerable Big Bang theory might be off the mark on several fronts. It's not just a single or couple of discrepancies. Astonishingly, this theory appears to miss the mark on a whopping 16 predictions, according to recent studies. The only prediction it accurately forecasts is the abundance of deuterium, a type of hydrogen variant. But wait, there's more to this intriguing deviation from predictions. The Big Bang theory, revered for decades, overestimates the quantities of helium by double and lithium by a staggering 20 times compared to what we observe in the universe. Additionally, this foundational theory stumbles when it comes to explaining the existence of massive structures in the cosmos. According to its principles, these structures should not have had enough time to form since the universe's inception. Adding to the puzzle, the theory struggles with its predictions regarding the density of matter within the universe. And here's an unexpected twist. remember those supposed asymmetries in the cosmic microwave background that were previously considered non-existent? Well, recent findings indicate that they do exist. It's akin to a cosmic plot twist, shaking the very foundations of our established cosmological understanding. Now, what's the remedy for these cosmic mysteries? Enter the JWST, a technological marvel that could potentially unlock the answers to these perplexing contradictions. While these discrepancies might seem like small deviations in the vast expanse of cosmic knowledge, they hold immense significance. Each anomaly is akin to a missing piece in our cosmic jigsaw puzzle, obstructing our comprehension of the big picture and leaving us with an incomplete understanding of the universe's nature and origins. These anomalies, unearthed by recent discoveries, are more than just glitches in our cosmic understanding. They shake the very foundations of what we've long believed about the formation and evolution of the universe. They challenge not just our comprehension of cosmic structures but also the fundamental fabric of spacetime itself. This, in turn, has profound implications for our understanding of universal expansion, gravitational waves, dark matter, and even the ultimate fate of the cosmos. Consider how a seemingly simple discrepancy, like the density of matter, could reshape our entire understanding. If this density differs from our predictions, it could reshape our understanding of how galaxies form and evolve, thereby altering our perspective on the role of dark matter in this process. Similarly, unexpected asymmetries in the cosmic microwave background could rewrite our understanding of the universe's initial conditions and the speed at which it expanded. But it doesn't stop there. These inconsistencies even ripple into our understanding of time itself. Currently, our perception of time is intricately linked to the evolution of the universe from the Big Bang onward. However, if the Big Bang theory is found lacking, it could prompt us to re-evaluate how we perceive time, its flow and its interconnectedness with space, challenging the reality of sequential time. The nature of time, a concept deeply ingrained in human understanding, poses a profound question. Does time exist objectively, or is it merely a construct aiding us in distinguishing between moments past and present? Some scientific theories propose a compelling perspective that challenges the conventional understanding of time, an idea suggesting that time might be an illusion fabricated by human memory. This intriguing theory posits that every event, past, present, and future, occurs concurrently. Essentially, everything that has occurred or will occur is happening simultaneously, transcending the linear flow of time as we perceive it. Consider this: while our intuition dictates that time moves exclusively forward, the laws of physics don't inherently mandate such a unidirectional flow. These laws hold whether time progresses forward or backward. The Big Crunch theory adds a layer to this speculation, suggesting that as the universe ceases its expansion and begins contracting, time might, in turn, reverse. Picture a scenario where the universe shrinks and grows hotter, akin to a reversed iteration of the Big Bang. The aftermath of the speculated Big Crunch poses an intriguing puzzle. Some hypotheses propose the emergence of a new universe through another significant Big Bang event. Others entertain the notion that our universe might reappear in a different location or form, akin to a cosmic bubble materializing into existence. The implications of these theories hint at a cyclic pattern, a continuum of expansion and contraction, potentially giving rise to an infinite succession of universes. This peculiar possibility challenges the conventional understanding of time, leading some scientists to a bold assertion: time, as commonly perceived, is a human construct. This assertion finds some support in Einstein's theory of relativity, which advocates for an interconnectedness between space and time. In this paradigm, the block universe theory posits that events across all temporal dimensions, past, present, and future, occupy coordinates within a four-dimensional spacetime continuum. Essentially, every event retains its reality within this interconnected framework. MIT physicist Max Tegmark beautifully encapsulated this notion, describing our reality as either a three-dimensional arena where events unfold over time or a four-dimensional framework where everything exists statically, unchanged, and immutable. If we subscribe to the latter perspective, time becomes an illusion, with the past, present, and future eternally coexisting. This concept challenges the traditional notion of a linear timeline and invites contemplation on the fundamental nature of existence itself. Julian Barber, a British physicist, presents a captivating take on time, envisioning our reality as a series of discrete now moments akin to individual snapshots in a photo album. In Barber's view, each moment stands alone, independent and unique, forming the fabric of our universe. He challenges the conventional perception of the past as a construct derived from our brain's memories. According to Barber, our sense of the past merely arises from our memories, creating an illusion of a linear timeline. In essence, the past might not exist as a concrete entity but rather as a product of our subjective experiences. Barber elaborates on this intriguing concept through his spatial theory. Within this framework, every now moment occupies a specific place within a vast conceptual landscape he whimsically dubs Plutonia. This landscape, governed by precise mathematical principles, exists outside the constraints of time, transcending temporal boundaries. Here, every point in Plutonia signifies a distinct now, embodying a timeless quality and challenging the traditional linear flow of time. This perspective, while revolutionary, draws parallels with the foundational work of Albert Einstein. Einstein's theory of spacetime serves as a cornerstone in our contemporary comprehension of the cosmos. His revolutionary insights intertwine space and time, reshaping our understanding of the universe's fundamental fabric. The contemplation of discarding Einstein's concept of spacetime might initially appear startling, yet such radical considerations form the essence of scientific progress. Science thrives on revolutions, constantly challenging, refining, and at times entirely replacing existing theories. This perpetual cycle of inquiry and discovery serves as the bedrock of scientific advancement. A glimpse into the annals of scientific history reveals this dynamic evolution. For over a millennium, the geocentric model held sway, positing Earth at the solar system's center. However, Nicholas Copernicus revolutionized this understanding by proposing the heliocentric model, relegating Earth to another celestial body orbiting the Sun. This groundbreaking idea gradually supplanted the long-accepted geocentric model, reshaping our cosmological perception. Following Copernicus, Isaac Newton introduced his seminal work on gravity. Newton's theory elucidated that all massive objects exert gravitational attraction, fundamentally altering our comprehension of celestial motions. This conceptual framework explained Earth's orbit around the Sun and the Moon's orbit around Earth based on mutual gravitational forces. Newton's gravitational theory reigned supreme for approximately 3 centuries until a watershed moment in 1915, the advent of Albert Einstein's groundbreaking general theory of relativity. Einstein's theory presented a paradigm shift, redefining gravity and spacetime. He postulated that massive objects like the Sun warp the fabric of four-dimensional spacetime. According to Einstein, this curvature dictates the paths of celestial bodies, giving rise to what we perceive as gravitational pull. The transition from the geocentric model to the heliocentric perspective, from Newtonian gravity to Einstein's general relativity, epitomizes the continuous evolution of scientific understanding. Einstein's spacetime theory has stood firm for over a century. Demonstrating its resilience against numerous challenges, a pivotal moment came in 2015 with the monumental detection of gravitational waves, a triumph that bolstered the credibility of Einstein's general relativity. However, even the most stalwart theories are not impervious to scrutiny. One of the most pressing challenges arises when Einstein's general relativity, built upon the concept of spacetime, encounters the realm of quantum physics. These two theories appear to operate under fundamentally different principles, creating a significant quandary within the scientific community. In the quantum domain, the rules diverge from the smooth, continuous fabric of spacetime envisioned by Einstein. Quantum mechanics introduces peculiar phenomena. For instance, a single particle can seemingly exist in multiple locations simultaneously. Erwin Schrödinger famously illustrated this with a thought experiment involving a cat, a vial of poison, and a quantum particle tied to a hammer. Until observed or measured, the particle's quantum state implies that the cat is paradoxically both alive and dead at the same time. This intriguing concept clashes with Einstein's vision of a seamlessly interconnected spacetime continuum. Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, highlighted this incongruity. According to Einstein's theory, a gravitational field cannot occupy multiple positions simultaneously. However, quantum physics suggests that matter and energy can exist in multiple states concurrently, leading to a perplexing disparity regarding the nature and localization of gravitational fields. Hossenfelder outlined the challenges of merging general relativity and quantum theory, especially at certain energy levels. Attempts to unify these theories encounter mathematical discrepancies, such as probabilities greater than 1, contradicting fundamental principles where probabilities are bound between 0 and 1. Moreover, calculations often yield answers of infinity, devoid of tangible physical meaning. This tension between two monumental pillars of physics, general relativity and quantum theory, poses a formidable challenge. The discrepancy between these frameworks suggests that a seamless unification might necessitate novel insights or even a paradigm shift in our understanding of the universe's most fundamental fabric. According to renowned physicist Michio Kaku, time does not exist as we perceive it. The James Webb Telescope has challenged our understanding of time, sparking debates about whether time is real or a human-made concept. Some scientific theories propose time as an illusion, with all moments happening simultaneously, defying our linear perception. Physics doesn't insist that time must only move forward. Theories like the Big Crunch suggest the universe could contract, reversing time, much like how the Big Bang began. What might happen afterward varies widely, from new universes forming to our universe starting over. These ideas propose a repeating cycle, challenging our conventional view of time. Einstein's theory of relativity connects space and time, suggesting they are part of a single four-dimensional framework where past, present, and future coexist. Physicist Max Tegmark describes reality as a static four-dimensional setup, where time as we know it may be an illusion, prompting a shift in how we understand existence. Harmonizing quantum and gravitational realms in physics has sparked a compelling quest for a unified theory that seamlessly merges quantum mechanics and gravity, akin to reconciling two feuding royal families. This pursuit has led theorists into the realm of intriguing ideas, with string theory emerging as a prominent contender. String theory suggests that the basic building blocks of tiny particles, such as electrons and quarks, are incredibly small vibrating strings, akin to the strings of a musical instrument, where different vibrations correspond to different particles. What makes string theory enticing is its potential to harmoniously unify general relativity and quantum physics. However, achieving this unity requires these strings to resonate across an astonishing 11 dimensions, 7 more than the familiar 4 of space and time delineated by Einstein's relativity. While string theory holds theoretical promise, it lacks concrete experimental evidence substantiating the existence of these additional dimensions. This absence of empirical validation has prompted critical scrutiny and debate within the scientific community, fueling skepticism and encouraging exploration of alternative avenues in the quest for a unified theory. Loop quantum gravity, LQG, offers one such alternative, aiming to reconcile conflicting aspects of general relativity and quantum mechanics. Unlike the smooth, continuous fabric of spacetime described by general relativity, LQG introduces a fascinating concept. Spacetime is not smooth but instead composed of tiny interconnected loops. Imagine a piece of cloth, smooth from afar but woven from threads upon closer inspection. Similarly, LQG proposes that spacetime, when examined at the smallest scale, resembles a network of interconnected loops or threads. It's akin to zooming into a digital photo, where what initially appears continuous is composed of individual pixels. However, delving into this minuscule realm poses immense challenges. At the Planck scale, an unfathomably tiny measurement around a trillionth of a trillionth of a trillionth of a meter, the structure of spacetime would be so intricate that a cubic centimeter could potentially contain more loops than there are cubic centimeters in the observable universe. Despite its intriguing implications, proving this concept remains daunting. Current technology is insufficient to detect structural changes at such a minute scale. Physicists assert that testing the Planck scale would demand a particle accelerator trillions of times more potent than CERN's Large Hadron Collider. To put the concept of the collider into perspective, imagine a machine the size of our entire Milky Way galaxy. That's the scale required for probing this unfathomably small dimension. While constructing a particle accelerator of that magnitude may sound like something out of science fiction, a consortium of physicists from the UK, France, and Hong Kong is exploring an innovative avenue to delve into these complex ideas. Their approach involves using an ultracold gas composed of billions of cesium atoms, forming what's known as a Bose-Einstein condensate. Their aim is to investigate whether gravity might exhibit quantum properties, a radical notion worth exploring. Interestingly, the vast expanse of the universe might provide an alternative method for detecting these tiny spacetime structures. Consider the light we observe from the farthest reaches of the cosmos, having traversed billions of light-years of spacetime. If there are minuscule imperfections in spacetime structure, this light could interact with them. Though each interaction would be subtle, the cumulative effect over immense distances might yield observable consequences. Over the past decade, astronomers have scrutinized light emissions from distant gamma-ray bursts in pursuit of evidence supporting loop quantum gravity. These bursts, stemming from the collapse of massive stars, exhibit intriguing anomalies in their spectral patterns that currently lack explanation. However, whether these distortions arise during the light's journey through spacetime or originate from the bursts themselves remains an enduring enigma. Sabine Hossenfelder highlighted this mystery, emphasizing our uncertainty regarding whether these distortions occur en route to Earth or originate from the burst sources. To unravel this puzzle, transcending Einstein's conceptualization of spacetime as a smooth, continuous fabric might be necessary. Einstein envisioned spacetime as an unchanging stage, independent of celestial actors like stars and planets. Yet, as we venture into the realm of quantum gravity, a fundamental rethinking of this notion becomes imperative. It's akin to not just altering the script but reconsidering the very stage upon which cosmic phenomena unfold. Redefining Spacetime, Laurent Friedel, Robert Lee, and George Hertzsprung, three forward-thinking physicists, have set the scientific world abuzz with their revolutionary take on spacetime. They propose that our conventional understanding of spacetime might be limiting, suggesting that it doesn't exist as a standalone entity but rather emerges from the interactions between objects within it. In simpler terms, imagine spacetime not as a separate fabric but as something that comes into being because of how things interact with each other. This fresh perspective challenges the idea that spacetime must be merged with the quantum world. Instead, it asserts that spacetime itself arises from the quantum realm. This shift in perspective is precise and groundbreaking, offering a new lens through which we can comprehend the universe. Why is this significant? Their theory might hold the key to unraveling a long-standing puzzle in theoretical physics known as entanglement. Entanglement occurs when two particles become intricately connected, so much so that changing one instantaneously influences the other, regardless of the distance separating them. This phenomenon seemingly contradicts Einstein's theory of relativity, hinting at information traveling faster than light, something Einstein famously referred to as spooky action at a distance. However, when viewing spacetime through the lens of this emergent theory, things start falling into place. If spacetime emerges from the quantum world, then the closeness between particles in a quantum sense becomes more crucial than their physical proximity. It's akin to feeling closer to a loved one far away than to a stranger nearby. In the quantum world, these non-local connections make sense, challenging our traditional notions of spatial distance. Friedel, Lee, and Hertzsprung have delved into this groundbreaking idea for the past 5 years, cautiously optimistic about their progress. Their approach is appealing as it envisions a quantum world with gravity, a departure from attempts to fit quantum rules into gravity frameworks, as seen in loop quantum gravity. Their next significant step involves incorporating time into their model, a critical aspect in understanding the fundamental fabric of the universe. While this might seem abstract and confined to academic discussions, the implications could profoundly affect our everyday lives. Our comprehension of spacetime influences our understanding of both gravity and quantum theory. Consider that our current technological gadgets rely on quantum theory. Therefore, a better grasp of the quantum structure of spacetime could pave the way for advanced future technologies, possibly revolutionizing various aspects of our lives. Much like the dethronement of a long-standing monarch, the reigning theory of spacetime might soon be challenged. Fresh contenders are emerging in theoretical physics, but it's challenging to predict which theory will ultimately triumph. However, when this scientific revolution does occur, it could herald a new era of discoveries, pushing the boundaries of our understanding of the universe.